Let's look at some further forces on inclined planes problems. So you're going to find this one's very similar to what we've already done, but there is going to be a little bit more of a challenging element to it. So let's have a look, see what we're going to do. So we have a particle of mass 8 kilograms. It's resting on a rough plane inclined at 35 degrees to the horizontal. Coefficient of friction between the particle and the plane is 0.2. A horizontal force P is applied to the particle with a magnitude that is just sufficient to prevent the particle from slipping down the plane. We want to find A, the magnitude of the force P, and B, the reaction between the particle and the plane. So let's start off, as we do with all of these problems, by drawing ourselves a nice, neat diagram that represents all the forces acting on the particle so that I can try and solve this problem. Here's my plane. It's acting at 35 degrees to the horizontal. Here's my particle. We have this vertical force acting down. That is my weight, because the weight of the object is 8 kilograms. So 8 kilograms, or 8g, because it's 8 times the gravity. Let's make this particle slightly bigger. Now at this point I always put in like a crosshair to represent the parallel and perpendicular. Notice, okay, it's not great, but this is just a sketch. Just want to try and keep it as neat as possible so that it's actually usable. Okay, so we have a normal reaction here because the particle is in contact with the plane, and that normal reaction is perpendicular to the surface, so it's perpendicular to the plane. I can fill in some missing angles. This angle here is 55 degrees because it comes in pairs of 90 degrees in a right angle triangle. This other angle here, that's 35 degrees because these also come in pairs of 90 degrees. We're told that horizontal force P is acting on the particle. So there's a horizontal force P. Doesn't matter whether it's pushing, doesn't matter whether it's pulling. Remember, we try to draw it so it comes out of the particle. Now we're told this horizontal force P acts and is just big enough to stop the particle sliding down the plane. So the motion would be down the plane. It's a rough surface, so this means that we'd have friction acting back up the plane. And just a note that the coefficient of friction is 0.2. Now the question asks to find the magnitude of this force P, and it also asks to find the reaction between the particle and the plane. Well, I've got no idea how I'm going to do this or solve this at the moment. There's quite a few unknowns here, and so the only thing that we can do is start off by resolving. Initially, I'm going to resolve perpendicular to this plane. Okay, so here we have resolving perpendicular. So perpendicular to the plane I have the reaction. Actually, what we're missing on this diagram is I should just really go around and complete all the angles. So that's 55 degrees because we know that that's a 90-degree angle. And this is 35 degrees because that's also a 90-degree angle. Now in this problem, because there's two forces parallel and perpendicular to the plane, and there's two forces horizontal and vertical, you could resolve in any direction you want. I tend to resolve parallel and perpendicular to the plane for all inclined plane problems, and there are mathematical reasons for this which we will come to later on. So I mean, my advice is to follow how I'm doing it, but if you do it parallel, horizontal and vertically, it will work just as well, and actually it will be just as challenging. So normal reaction, acting perpendicular to the plane, we can forget the friction because that is parallel to the plane, so these two forces at right angle don't interfere with each other. But what I need to do is both the force P and the weight acting in the opposite direction to the reaction, and I need to resolve their components. So I get minus 8g, and then cos of the angle I turn through, so cos of 35. And then I get P, so minus P, and cos of the angle I turn through, so the angle I turn through is 55 degrees, so cos 55. And this is equal to 0 because the system is in equilibrium. Now what I'm going to do is I'm going to rearrange this to get an expression for R. So I'm going to add 8g cos 35 to both sides. And I'm going to add p cos 55 to both sides. So we get r is equal to 8g cos 35 is 64.222. Just going to work to 3 decimal places. This is going to be quite complex. I should imagine this is probably going to be simultaneous equations, so I'm just going to simplify things a little bit now. And then cos of 55 is 0.574, so I get 0.574p. Okay, now having resolved perpendicular to the plane, I can resolve parallel to the plane as well. What I'm thinking is when I resolve parallel to the plane, and actually this is where my strategy actually changes from perhaps the last example, I don't necessarily just resolve blindly parallel to the plane as well. What I'm thinking about if I resolve parallel to the plane is I'm going to get another equation, but this time it's going to be in f and p. And I don't really want to have 2 equations in 3 unknowns. So what I'm going to do instead is I'm going to find my friction using mu. So I know F equals mu r, and so I can say that F is equal to 0.2 times 64.222 plus 0.574p. And so when I work through that, I get that my friction is equal to 12.844. So I'm just expanding the bracket. I've multiplied 0.2 times 64.222, and then 0.2 times 0.574 gives me 0.115p. Okay, now the reason I've done that is because now if I resolve parallel to the plane, so let's resolve up the plane. What happens is instead of putting the friction in, I can put 12.844 plus 0.115p. So I can put this expression in for the friction. I then have P acting up the plane. So I can add this force, P. Remember, it's not just the whole force P, it's the component of force P. So I want to do P times cos of the angle I turn through, so cos 35. And then finally, I want to finish off, because this weight is acting down the plane, it's in between the downwards direction and the opposite direction to the reaction. I'm going to get minus 8g cos of the angle I turn through, so cos of 55. And this is all again in equilibrium because it's on the point of slipping, so it's equal to 0. Now, you can see the benefits of writing or getting the friction as an expression in terms of P, because now instead of having an equation here that is in terms of F and P, I've just got an equation which is in terms of P. So I've got the 0.115p and the P cos 35 here. So let's tidy this up. I'm going to tidy up and collect the P's together in a moment, but also I'm going to collect the 12.844 and 8g cos 55 on the other side. So first of all, I'm going to add 8g cos 55, and then I'm going to subtract 12.844 from both sides of the equation. Now, if I evaluate cos 35 on the left hand side, what we get is 0.115p is not equal to, so apologies, let's get rid of that, 0.115p plus cos 35 of p, which is 0.819p. This is now equal to 8g cos 55 is 44.968 minus the 12.844. Okay, so that's just a rearranging. So the intermediary step. What I want to do now though is I want to collect the p terms so that I get that on the left hand side I get 0.934p is equal to, and on the right hand side when I find a difference between these two values I get 32.124. And so I just have this final step now, as if I divide by 0.934, we finally get that P is equal to 34.4 newtons. And this is to 1 decimal place. Okay, we're part of the way there now. So let's just tidy that up a little bit so make it a little bit clearer. 1 dp. Okay, so we've done part A. I'll label that as part A. In fact, by doing part A, we've done most of part B, because all that's left now is that I want to find the normal reaction. I can use this equation right back at the beginning here, because I formed this equation for the reaction in terms of P. And so it's quite nicely, all I have to do now is say, okay, well, R is equal to 64.222 plus 0.574 times 34.4. Now, I wouldn't actually use 34.4, I would be using the stored value on my calculator so that I can get as accurate an answer as possible. And when you work through and work it with that accurate answer of your calculator, you should get an answer of 84.0 newtons to 1 decimal place. Okay, well, I hope that made sense and that you understood the problem.